Today, we're going to start our new unit studying right triangles with a quick review of Pythagorean theorem, and we're actually going to apply its converse. So if you think back to logic, converse is when we kind of switched our order, like converse is switch, inverse is not. So we are used to thinking of Pythagorean theorem as if we have a right triangle with two legs and our hypotenuse C, well, then we have already been taught, and we've used this before, that a squared plus b squared equals c squared. So our converse is when we switch our order. So if we plug some lengths that were given for a triangle into a squared plus b squared equals c squared, and it completes the Pythagorean theorem, we get a valid equation, well, then that's enough to prove that we have a right triangle. And so we're going to apply that to a few problems today. But first, let's review Pythagorean theorem. So again, with a squared plus b squared equals c squared, c is always standing for our hypotenuse in our triangle. And so to find that, always look for the right angle and look for what side is opposite from that right angle. So in example 1, we're looking at a triangle ABC, where we have side A on the left side. Also, we could call that segment BC. And we need to solve for that side, given our leg 12 and our hypotenuse 13. And I know that that's the hypotenuse, because if I look at my right angle and kind of use that almost as an arrow, it points towards my hypotenuse. So if I fill into my a squared plus b squared equals c squared, well, I'm just going to go ahead and use a, since that's our variable in our triangle, plus 12 squared, our other leg, should equal 13 squared. So if we multiply that out, a squared is plus 144, and then 13 squared gives us 169. Subtract 144 from both sides. So a squared will be 169 minus 144, otherwise known as 25. And then to get a by itself, we need to take the square root of both sides. And so our solution comes out to be 5. So our missing length is 5. Okay, in our second triangle, we have two legs filled in, and we're missing the hypotenuse on this one. So we're still going to start the same way. So a squared plus b squared equals c squared. But in this case, we know both of our legs, so we're going to fill those in for the a and the b. Again, the order doesn't matter as long as those are on the same side of the equation. So 20 squared plus 30 squared equals c squared. Well, 20 squared is going to give me 400. 30 squared will give me 900. How did I do those so quick? Okay, well, you think about it. Well, 2 squared is 4. And then we have a 20, so we're multiplying a couple extra zeros or a couple tens in there. Okay, well, 400 plus 900 gives us 1300 is c squared. And same as before, we need to take the square root of both sides. And if I double check that on my calculator, square root of 1300 does not come out as a nice variable or a nice value. So we could write this two ways. So we could simplify out our radical, again, something that you may have done in Algebra 1. And so we could write this as, well, 1300 is the same thing as 100 times 13. But 100, I picked that out specifically because he's a perfect square. What's the square root of 100? That's 10. But 13 doesn't have a perfect square. So I could write that as 10 root 13. So that's one possible solution for C. Or I could write it as a decimal, and the decimal value that comes out is 36 point, I'm going to go 2 decimal places, 0.6. So either of these would be a correct answer. And you might see in this unit, problems that have decimal versions for their final answer and some that might have this simplified square root. Well, don't forget too, if you know how to express the answer as a decimal, but you see the reduced radical problems, don't forget you could always just plug that into your calculator and figure out the decimal equivalent and use that to choose your answer. So either one would be fine. Okay, now would be a good time. Go ahead, pause the video and try out at least examples 3 and 4, just to see if you remember your Pythagorean theorem. All right, so real quick, let's look at 3 and 4 and then 5 and 6 for slight application on this. So example 3, we have two legs that are 3. Our hypotenuse is x. So I would set this up as 3 squared plus 3 squared equals x squared, otherwise known as 9 plus 9 equals x squared, or 18 equals x squared. And so if we take the square root of both sides, again, two ways we could express this. So we could express x as, well, 18 is the same thing as, off to the side here, 18 is the same thing as 9 times 2, and 9 is a perfect square. Perfect square root of that is 3, with that leftover 2. Or we could express as a decimal, and the square root of 18 is approximately 4.24. Okay, number 4, we're missing a leg. So a squared, or we could use x squared, plus 9 squared equals 15 squared. And again, your x squared and your 9 squared could flip-flop. It really doesn't matter. But notice every single time I do these problems, I'm always simplifying out before I start moving things around. So 9 squared is 81. 15 squared, not one I have memorized, is easily 225. Although that would definitely save you a lot of time if you could memorize your perfect squares. Okay, subtract your 81. So that's going to give us 144. And I remember that, that's my 12 squared. So when I take the square root of both sides on here, my x comes out as exactly 12. Okay, 5 and 6 really aren't all that different. It's just that our right triangle is kind of hidden in the diagram. So as long as we can pick that out, we can still apply Pythagorean theorem. So in number 5, again, pretty easy to ignore the rest of the triangle. My x is a hypotenuse, so I could set up 16 squared plus 33 squared equals x squared. Well, 16 squared is 256. 33 squared, 1089. Large numbers on this one, but that's okay. So adding those together, 1089 plus 256, there we go. 1345 equals x squared. So again, to isolate your x, you need to take the square root of both sides. And again, you'll notice I'm flip-flopping where my x is. It really doesn't matter what side you write it in. Okay, now 1345, I don't believe that's perfect square root, but let's test it out. Let's see what happens. Nope, it comes out to be approximately 36.67. And we could go through and do our factors on that one, but a decimal answer is just fine. Okay, number 6, again, the triangle is just kind of hidden in another diagram, something called technically we're looking at a rhombus on this one, which we'll come back and look at next unit. Okay, but again, we're missing a leg, so let's just plug in. So we have an x squared and an 11 squared are 2 legs. Our hypotenuse 28 because that's directly opposite from the right angle. Okay, 11 squared, 121. 28 squared, 784. Okay, subtract out your 121. 663. Take our square root of both sides. 663. Again, not a nice number, so I'm going to go approximately equal to because I need to round off. So 25.75 approximately. Okay, be careful with your rounding. Don't forget, if your last digit that you want to write down, the next value, if that's a 5 or greater, you need to round up. Alrighty, so we've already talked about Pythagorean theorem before, so let's look at this converse and how we could use this. And so we know c squared for Pythagorean theorem is only going to equal a squared plus b squared if we know we have a right triangle. So what happens if it doesn't? And so we can actually look at our right triangle, our Pythagorean theorem results, and use that to actually predict what kind of triangle it is without knowing any angle measures. So if we start with if c squared is equal to a squared plus b squared, well, then our Pythagorean theorem is correct, and we know we have a right triangle. However, what if it doesn't? So our two scenarios could be, well, what if c squared is smaller than a squared plus b squared? And what if c squared is bigger than a squared plus b squared? So think about a right triangle. So you have perfect right angles going on in your triangle. So your hypotenuse, imagine that's the end points of my pens. Well, what happened if that was too big? What happens to our right angle? If it's bigger than 90 degrees now, what kind of triangle would we really have? Or what kind of angle would we have where right angle was supposed to be? We'd have an obtuse triangle. Well, what if that hypotenuse is too short? Well, that means I'm kind of shrinking down my angle. So now instead of a 90-degree angle, I'm something smaller, which would be acute. So if we plug into Pythagorean theorem and our hypotenuse is too small, which would be like our second statement, then we're going to have an acute triangle. Versus if our hypotenuse is too big, our third statement, well, then we're going to have an obtuse triangle. And don't forget, too, we're still trying to make triangles in here, so we can't forget that relationship that any combination of sides, we need to be able to add two of the sides together and have them bigger than the third, no matter what sides we're using. So never a bad idea to go through and test that as well. So let's try this out on some problems. So here we go. Example 7, we are going to determine first if we even have a triangle in the first place, and then second, if those sides actually make a right triangle. So 3, 7, 9. Well, if I add my two smallest sides together, the 3 and the 7, well, 3 plus 7 is 10. That one definitely makes a triangle. So I can test now whether or not it makes a right triangle. Okay, so 9 is my biggest side. It would have to be the hypotenuse. So I'm going to test out 3 squared plus 7 squared compared to 9 squared. Well, 3 squared is 9, 7 squared is 49, and I add those together and I get a 58. 9 squared is 81. So compared to the hypotenuse, 58 is smaller. In other words, our hypotenuse is bigger than, if I'm using my inequality, alligator eats the bigger number, that 81 is bigger than 58. So that means I have an obtuse triangle. So again, I'm going to scroll back up to my rules. So you'll notice alligator eats the bigger number, open part of the inequality was towards the inequality or towards the hypotenuse. That's what we're looking for obtuse triangles. Acute triangles, we want it to go the other way. So let's see what happens with number 8. Well, first off, do they make a triangle? So 20 plus 21 gives us 41, definitely bigger than 29. I know it's a triangle, so that's not even an option. Okay, let's test it out. So 20 squared plus 21 squared, we need to compare that to 29 squared. Well, 20 squared is 400. 21 squared gives me 441. And 29 squared gives me 841. So if I add together my 400 and 441, that gives me 841. Hey, wait a second, that is exactly equal to 841. So that means that one works with Pythagorean theorem. That is a right triangle. All righty, example 9. Which two sides do we have to check to make sure it's a triangle first? These guys are out of order. So I need to test the 4 and the 11, the two smallest sides. Those give me a 15. And unfortunately, 15 is smaller than 16. So does this one make a triangle? Nope, not a triangle. Okay, number 10, again, out of order. 17 and 17, well, put those together, I get a 34. 34 is definitely bigger than 22. So I know this does make a triangle. Now I just test which one. So 17 and 17 are my smaller sides. They would have to be the a squared and the b squared. So 17 squared plus 17 squared. And we need to compare that to 22 squared. Alrighty, 17 squared is 289. 22 squared, 484. And so 289 plus 289 gives me 578, which is larger than 484. Now 484, that was our hypotenuse. So it's smaller than the rest of the equation, which means we have an acute triangle. Okay, go ahead and pause the video and try out examples 11, 12, and 13. You'll probably have one of each, but you never know. So you want to go all the way through your process to figure that out. So you'll notice I went ahead and filled in my math behind these problems. So let's make sure that you are interpreting your answers the same way. So in number 11, I double checked, well, 31 and 35, those definitely add to be bigger than 39. I don't really need to even do the math for that one. And then when I plug those into Pythagorean Theorem, get for my hypotenuse, the 39 squared, I get 1521. And when I add together my two legs squared, I get 2186. So definitely adding my two legs together is bigger than the hypotenuse, aka the hypotenuse is too small. So that means I should have an acute triangle. In number 12, again, my numbers were out of order. So to test if it makes a triangle, I'll have to add the two smallest values, the 8 and the 15, except those add up to be equal to 23. So we do not have a triangle on this one. Darn it. In number 13, it was kind of close, so I did double check that, and 11 plus 19 should give me 30, which is bigger than 28, so we can go ahead with this problem. And then our legs squared gives us 484, whereas our hypotenuse, or what would be the hypotenuse, 28 squared gives us 784, which is definitely bigger than the 484. And again, the 784 represented what would be our hypotenuse, but is it? It's too big. It is larger than the legs squared, so that means that's an obtuse triangle. Alrighty, so the last piece we need to look at is if we have whole numbers that are given and we know that they satisfy Pythagorean theorem, we know they make the right triangle, technically we can call these something called the Pythagorean triple. And so you may have seen I've used the combination of numbers 3, 4, and 5 a few times throughout the year because A, I know they make a triangle, but specifically, if I test it out, 3 squared plus 4 squared compared to 5 squared, well, 9 plus 16, that equals 25. 3, 4, 5 makes a perfect right triangle. And in fact, I can cheat the system a little bit because if I notice that 3, 4, 5 make a triangle, if I put that together with what we just talked about for similar triangles, I know a triangle that's twice as big would still be a right triangle, or 3 times as big, still a right triangle. And so I can look at those multiplications, those multiples rather. See, 2 times would give me 9, 8, and 10, or multiply them times 3, and I'd get, oh, that was times 3. Multiplying them times 2, I would get 6. Ooh, I'm getting ahead of myself. Let's start that over. So times 2 would give me a 6, 8, and 10. Times 3 would give me a 9, 12, and 15. And I could keep going and make a whole bunch of different triples. So, people have gone through and tested all possible combinations, and the ones that are used most often, especially on like the SATs, or if you need to take the SOL, keep an eye out for these triples because you don't need to test them. We already know that they make a right triangle. So one triple is 5, 12, 13. So if we kind of do a scale factor of 2, we could have 10, 24, 26. Or if we did scale factor of 3, we could do 15, 36, 39. And those make a right triangle. Next most common is 8, 15, 17. So times 2, that would give us 16, 30, 34. Or times 3, we'll have 24, 45. This one I need my calculator for. 17 times 3 gives me 51. Again, not a value that you'd necessarily think of, but if you can boil it down to that 8, 15, 17, you might recognize it. Okay, another triple, again, not as widely used, but it might show up. 7, 24, 25. So multiple of 2 would be 14, 48, 50. Or multiple of 3 would be 21. Let's see, 24 times 3 gives us 72 and 75. So neat little trick to recognize these. Alrighty, Feel free to go ahead and stop the video, but if you would like to see some additional examples for Pythagorean theorem, keep watching for the last two. However, you have plenty of information to be able to start working on your practice. So if I don't talk to you, have a great day. If not, pop back into Zoom with any questions that you have.